About a few months back, I decided to embark on the blockchain technologies certification by MIT, that's Massachusetts Institute of Technologies. This 6 weeks course proved to be a very resourceful learning for myself. There were many concepts learned from the blockchain which gave me a very in-depth perspective of what the fundamental blockchain is about and how the blockchain initiatives can improve the different aspects of our lives. In this MIT Blockchain Technologies course, I was exposed to an online blockchain demonstration, which I would want to share in this video. I believe that from this online demonstration, you are able to understand the fundamentals or the building blocks of the blockchain better. Hello YouTube, I am Eugene Ying with Blockchain 360. If you find this topic interesting, please do watch to the very end of this video. This is a blockchain demonstration on the website indepth.com. For the beginning part of this demo, I will first explain about the building blocks of cryptography. It is the SHA-256. SHA-256 is secure hashing algorithm and is part of the 2 series. It was created by NSA around the year 2001. It has never been hacked. For your info, online secure payments with SSL certs such as PayPal, standard online e-commerce payments, online bank transfers are now based on this SHA-256. In fact, the online payments started using SHA-256, migrating from the 1 series somewhere in 2014-2015, whereas the first open blockchain launched, that is the Bitcoin blockchain, adapted the SHA-256 as its building block in 2009. Hash of an entry is like a fingerprint of the word. It will be unique. For example, my friend enters her name Mei Lun. You will see the results gives a hash, or rather a fingerprint of a 64 string of codes that start with 6B96. We then enter my name Eugene. The hash will be a different string of codes. This is the 64 string of codes that start with F5A3. Therefore, every entry gives a unique hash fingerprint. We also need to take note that it will always be the same for the same entry word. For instance, we enter the number 1. The fingerprint for 1 is a string of codes that start with 6B86. We then enter the number 2. The hash for 2 is D473 as its first 4 characters. But when we go back to the entry number 1, we will notice that the hash is again 6B86. Because the hash output is unique and always the same for the input, there is no way to backguess the entry input to figure out the output hash fingerprint. For example, let's say we have a riddle. What is the input such that the output is with the string of codes that start with 0000? That is initially 4 zeros. We have to just make random guesses starting from 1 to 2 to 3 and so on, until we get the hash output with the first 4 digits, which are zeros. This can take a very long time because it takes a long time to solve this riddle. We have powerful computers to insert random input numbers at a very fast rate to solve this riddle. Henceforth, the powerful computers are also known as mining machines. Let's extend this to a block. At the block tab page, we see that a block will consist of block number, nonce, data, and hash output. The hash will be the hash fingerprint of all the above 3 fields combined. That is the block number, the nonce, and data. The data is the data entry of the project or blockchain initiative. For example, it could be, say, the tabulation of the total number of HIV infected patients in a particular country. Let's say this is 5. Nonce is the guess which the verifier or blockchain miner needs to enter such that with these 3 data, the algorithm will produce a certain hash combination. In this case, it is 4 zeros for its first 4 digit of the hash. Only when the hash is with 4 zeros as the first 4 digits will the color of the block be green. Now the color is red. The verifier or miner knows that the nonce is not correct. To get the correct nonce that will verify the block to green, the miner will have to keep on inserting the nonce value until the correct nonce entry will yield a green block. So to illustrate, the verifier or miner, say, enters a 1, the hash is not 4 zeros, the block is red. The miner goes to enter another guess, say 2, the block stays red. The miner can continue to make guesses until finally the block can turn green. As this is very time-consuming effort, powerful computers, not humans, called miners, does this verification work. So in this illustration, we hit the mine button, simulating that these powerful miners keeps on trying the random input until the hash has 4 zeros as the first 4 digits. Here you see that after clicking the mine button, the block will end up being green after a while, indicating the block is mined. From one block, we enter this demo to a chain of blocks, blockchain. So in the chain of blocks, we have the block number, the nonce, and the data for each block. Let me explain how each of these blocks are tied to one before it is a chain. The one before it is a chain. After being mined, the hash is used as the field for the next block, as seen the field title PREV, previous. So we mine each block, hence the security of the block are all interconnected. Let's say we have the data for the 3 blocks 1, 2, 3 as 5, 6, 7. For the miner to verify the entire blockchain, the miner has to mine the first block. Once that turns green, the miner then mines the second block and then the third block. Now let's say there is a compromise. Someone tries to alter a mined block, say the first block data. From the data 5, it's altered to 50. Because of this alteration, the entire chain of block goes red, especially the last block 3. If the miner wants to allow the blockchain to accept this alteration or reorganize the blockchain because of these alterations, the miner has to spend a lot of energy and effort to remine all the blocks from the affected block to the very last block in the chain. This is the reason why we say that the data in the blockchain is immutable or resistant to modifications. It just takes a lot of effort or is very expensive to remine all the blocks and not just the affected one block. Therefore, the data stored in the blockchain is secure and safe. Before I go, just want to let you know that I do give free webinars on Bitcoin basics and on the blockchain. In my webinars, I do also introduce FPGA mining with returns of 10% or more monthly. I'm mining with Dunamis. It's transparent, safe, and reliable. The reason it is transparent is because Dunamis is a registered and regulated co-location company in the United States. It does not sell mining contracts as per se, but rather high-capacity security mining space. Therefore, our mining machines, the co-location service, and the low electrical fees of 5 cents per kilowatt hour is charged separately. With the low electrical fees of 5 cents per kilowatt hour, it is then possible to gain more than 10% per month. Do explore my free webinars. The link to the webinar schedules are shown in the description below. That is all we have for this video. I sincerely hope you have enjoyed this sharing. If so, please punch the like button. If you have any comments or questions, please post them below. Until the next video, continue hodling and have a fantastic week ahead. Bye.
Blockchain 360.